Let's try this again. See if this will work. We're going to play with some numbers here. Yeah, let's see. There we go. And this only gave me limited information, so we'll have to kind of make some stuff up on the fly. But we'll work through that. It'll be okay. So what I want to do is take a look at barium 137, barium 138. We've got the percent of those individual isotopes listed there. So 137 is 11.2, 138 is 71.7. And now what we're going to do is hide all that. 137, I already forgot, 11.2. 138 was what? Okay, cool. Let's say at 87.8%. We're just going to hope for the best. We'll just go from there. So this is for barium. So if that's the information we got, does that total to under 100? It does, right? Okay, so that's good at least. If these were our two isotopes and that was the information we had, what would be the atomic mass for barium? How do we figure it out? Ideas? What do you got to do? Whoops. So, do we know the mass of A? Yeah. So what's the mass of A? What's the mass of A? We'll go with 137. This is going to be a little bit off because that 137 is technically the mass number, not the actual mass. But that's all I've got based off the quick search I just pulled. Do we know the percent of A? 11.2. So we could write this in as 11.2 per 100. It's perfectly acceptable, or you could immediately convert that into your decimal 0.112, which I'll do with the next one. Plus the mass of B, 138, times the percent of B. What was the percent of B? So we could write that as our decimal value. All right, now what do we do? Yeah, just multiply and add it up. Okay, I do kind of need a number here. I have not done this question before, fully off the fly, so I don't have any of that, what that numerical value is, but I would like a numerical value because we need to be able to discuss that. Yep.
A is 15.344. And B is 121.164.
164. Close enough. Add them up. $136. That's what happens when you try and do something on the fly. Does that average value make sense? Why not? Okay. So why should it be lower? If it's an average, it should be dead between those two values, our 137 and our 138. We should have 137 point something. It should be there. It's not. Why is it not? Okay. But we should be able to do a little bit better than just the percentages aren't correct. Okay, so those are totaling up to what, 93? It's 97, 98, I don't know, 99, show off. So it's less than 100%, right? So we're missing some mass that would then contribute to this, and that mass could add to this. Okay, does that make sense so far? Of that missing mass, do you think it has a smaller value than our 137, 138, or a larger value? Why do you think it's smaller? Okay, so we're probably looking at other isotopes of barium existing in that barium 136 range, okay, maybe even 135. Does that kind of make sense? So what we're trying to do is manipulate the numbers we've got, see where those systems are at, and try and build that into place. Kind of, sort of? Okay, but ultimately with these types of questions, this is what you're given: the mass of A, mass of B, percent of A, percent of B, and you're either finding your, and we know that equals the average. Okay, so you will be asked to solve for one of those numbers, period. Okay, so as long as you know that formula, you're set. Okay, barium gets a little bit trickier because there's more than two isotopes. I only picked two because I only expect you to deal with two. Okay, how would you adjust the formula if you had more than two? So this was talked through, believe in the videos, is that you would add however many masses were necessary in that system, percent C, okay? Plus so on and so forth until you got your average. Make sense? Okay. That was really the only question I could come up with on the fly to deal with mathematics and calculations on it. So we're kind of stuck with that as far as the big mathematics. Are we good to delete everything? Okay. I think that erases everything. Go back to my desktop. And since we're on Wikipedia, I know we did it really fast, but if we take a look at that table, there are other isotopes for barium, right? And the other isotopes for barium all happen to have smaller masses. Neat, good job. Okay, so we get some internal consistency. How else could we go through and ask this? Because if you ask me, that's kind of annoying to have to deal with all the mathematics. It is part of the class, so you'll have to deal with mathematics at some point or another. But it would be nice if we could ask questions that didn't involve having to just do the rote math, because that rote math is something that you could just memorize, formula, plug and chug, and be done with. Okay. Are there ways that you could interpret isotopes that don't rely on mathematics? Okay. Yeah, we got a couple questions that they're randomly highlighted. So I just wanted to find them so I knew where they were at. Okay, so if we look at this question, which of the following compounds is not physically possible? So I'm going to go way out on a limb right away and say this question is technically wrong. Why? It's a technicality. So if you raised your hand and was like, this is wrong during the test, I'd be like, tough, just change that word, it's fine.
Is it the word physically?
Nope. To be a compound, what do you need? You need at least two or more elements. None of these are two or more elements. These are single values. Okay, so if we're looking at isotopes, okay, how do we know we're looking at isotopes? Because we started asking about isotopes. Okay, well, that was the easy answer. Now the hard answer. What about this question tells you should be thinking about isotopes? A couple people talking. Heard here.
I don't know, but is it because there's only one element in every answer?
Nope. So the number of neutrons does have to do with isotopes, but I don't see anything telling me the number of neutrons. You want to add more to that, or are you going to leave it at that? Okay.
Is it because, so like, if I look some of those up, like phosphorus, it has the numbers way more than the atomic number, so I
Okay.
know that has more
So let's talk through that. The very first statement was, if I look some of this up. Okay, we got a response there. That was a good, appropriate response. Why is that a problem? You can't look them up during the test. You want to follow up with what you're talking about when you're looking them up?
Meaning periodic table.
Okay. Cool. If we shift to the periodic table, could we get some more context out of this? Yes. Okay, but what's the periodic table tell us? It tells us germanium.
32.
32 what? It also says 72.64.
32, the atomic number is 32.
Cool. Okay, this says germanium 32. What does germanium 32 written on the exam mean in comparison to the periodic table that tells us germanium 32? We'll just write it all down so we can all be looking at the same thing, more or less. So that's our periodic table. And the exam says germanium 32. Yep. That's where I thought you were going with neutrons at first. This notation is the name followed by the mass number. Okay, that's in specific reference to isotopes, a particular isotope with that matching mass number. So if we're saying name dash mass number, what is the mass number? Okay, as was suggested, this is the protons plus our neutrons. If we wanted to get real fancy, we could put the charges in the upper right-hand corner. Okay, so if I go to the periodic table, what does the periodic table tell me? About anything. That 32 tells me this is the number of protons. Periodic table tell me anything else? So that's my atomic number. Say again? Okay, this would be the atomic mass, which is the average of all the isotopes. Okay, we're only being asked about one isotope, so that average is probably going to be misleading. Okay, so does anything stand out to you yet?
You can answer it.
What?
I can answer it.
Okay, so you, no, okay, you don't get to talk. Does anything stand out to anybody? Yet. Okay. Theoretically, something stood out to him. I don't know. We'll find out in a little bit. Okay, but we're not going to find out yet. So let's take this information and kind of continue to manipulate through our system. So let's summarize what we've got here. So that first answer for germanium 32, we have 32 being our mass number, which is our protons plus our neutrons. Yeah? And the periodic table told us we had a 32, our atomic number. What does the atomic number represent? Okay, number of protons, right? So we've got that information. So let's go ahead and move to the next one. It says sulfur 32. So the 32 from in front here, we'll call it 32 underline, represents what?
Mass number.
That represents our mass number. Come on, pen. I want blue. Thank you. Okay, that mass number is again our protons plus our neutrons. What does the periodic table tell us?
That sulfur has 16 protons.
That sulfur has 16 protons. Anything stand out to you yet?
You have to go through and do the equation for each isotope to figure out if the number of protons, neutrons, and electrons makes sense.
Okay, so we're getting a suggestion that we need to go through an equation. You could, potentially. And in that equation, you would try and figure out the number of protons, neutrons, and electrons. So first, do we need an equation to tell us the number of protons?
No.
No. Do we have an equation to tell us the number of electrons?
Yes.
Within the context of this question, there's no information whatsoever. We know nothing about the charge. So all we could assume would be our electrons are the same or they're irrelevant to the question. Do we have an equation for the number of neutrons? Yes. So we could figure out the number of neutrons in each of these cases, yeah? Okay, so you want to go through and do that? How many neutrons for our sulfur? 32 minus 16 gets us 16 neutrons, right? So that's memorizing our formula. How about for germanium? We have 0 neutrons. We'll ask again, does anything stand out to you yet? You're not allowed to respond. I already told you no. Yeah? No? Okay. If we're still no, that's okay. We've got a third answer that we could look at, and we would hope by that third answer we get to enough context that we could be able to come up with something. Because we've got 2 more answers after that that are all not or all are. And that's going to really suck if we can't differentiate any of these things, right? Okay, so let's look at that third answer. If I can get my pen to change colors. Green, we have phosphorus 32. Okay, so what does that tell us? We got the 32 underlined coming from the name, which means that's the number of protons and neutrons. What can we pull from the periodic table?
15.
Number of protons are 15. We do that math and we get 17 neutrons. So now again, we ask the same question. Does anything stand out? One of these is equaled out to 0. Okay, so is there a difference between these 3? Yes. Since we do have a difference, what does that suggest about answer choice D and E? They're probably wrong because we're able to differentiate some of these things. Okay, so now the question becomes, what is our answer? Okay, and we could play the game of Sesame Street, which one of these things is not like the other? And that is A, germanium. And of course, since we decided that A, germanium is the one that's most unlike everything else, of course it is actually the answer. Yes, it is. So now the question is why? I have no idea who's talking. Okay. Do you agree? Okay. When we're talking about atomic structure and we build these things out, okay, when do you first see the existence of a neutron? It's in the nucleus, but when? What atom has a need for a nucleus? It's kind of a tough question, and we could go to the periodic table to help us out. Okay, because our periodic table does give us information, ballpark, about the protons and neutrons. Where does it give us information about the protons and neutrons? In the atomic mass. It's officially an average, but it gets us pretty close. If we take a look at hydrogen, we know hydrogen has how many protons? 1. What's its atomic mass? 1, which means the vast majority of the time, how many neutrons do I have? 0. Because both the protons and neutrons contribute to mass. What happens when we move over to helium?
2 protons.
I have 2 protons, and now my atomic mass is 4, which means what did I have to add? Neutrons. When do neutrons come into existence?
After hydrogen.
Right after hydrogen. Hydrogen is the only element that doesn't need neutrons. Why? Where is the neutron? In the nucleus. What else is in the nucleus? Protons. And what's going to happen when I take a positively charged atom and bring it near another positively charged atom? They repel. So if I take a proton and put them near each other, they're like, nope, and they're going to spread apart from each other. Except what is a nucleus? The nucleus is where I take all of my protons and I smash them all into an infinitely tiny space. How could I possibly do that without the atom exploding? I add neutrons. Okay? So what we're looking at within this manipulation is, do we understand that we actually need neutrons to build this out? So some students will go through and try to predict based off of the atomic mass. That's the wrong direction because you can have tons of different isotopes with the varying amounts of neutrons. Okay? Neutrons is just an extra particle there that really doesn't contribute anything other than mass. Okay? So for the sake of hydrogen, yeah, the vast majority of hydrogen just has the one proton and no neutrons. But could I have two neutrons? Yeah. Or sorry, one neutron? Yeah, I can. Okay? And when I add one neutron to it, that becomes hydrogen, but now heavier. And so we could call it heavy hydrogen. Have you heard of heavy water before? Okay? Do some nuclear radiation type stuff, and they'll talk about heavy water when they're talking about power plants. Okay? What's happening is the nucleus gained a neutron. So you could get deuterium. That's now going to make water heavier than normal water because it has an extra neutron. It has twice the mass. Could I add another neutron to it? Yeah, why not? Okay. It's still hydrogen, it's just now weighing 3 times as much. Okay. And because it's now the simplest element, when we do things and study those things, sometimes we'll come up with names. So you may have heard of the quote-unquote element deuterium. Does that sound vaguely familiar? Deuterium is hydrogen. It's hydrogen with an extra neutron, that's it. And then the one that more people have heard of, which is even more rare, tritium. Does tritium sound familiar? That usually makes its runs through sci-fi stuff. Okay, tritium is hydrogen with 2 neutrons. Tri for tritium, right? Tri means what? 3. How many neutrons does it have? But it's tritium. If it only has 2, it's because the mass of it is 3. 2 neutrons, 1 proton. That's your tritium. Yes, sir. So, fun question on that is how do we actually get more neutrons? Okay, I would actually flip that. How did you get more protons? I mean, you're now asking the question of where is it getting more neutrons? Well, why did I get more protons? Okay, where most of this is happening is you're looking in the sun. And what's the sun made out of? Lots and lots of hydrogen and lots of helium. Yeah, it's also there. Okay, very high quantities. And you're looking at immense pressure due to mass, gravity, pulling everything in. And what's happening is that force is drawing those hydrogen atoms closer and closer and closer to each other until what happens? Sort of, they collide. They collide so much that they fuse, and that's where we're looking at fusion. And that fusion usually results in the loss of heat, and that's where we're getting that light coming off of, or the heat coming off of it. But now I don't have 2 atoms of hydrogen anymore. I have 1 atom, but it can't be hydrogen. It's now going to be helium because it has 2 protons. Okay, so when we're looking at the creation of those, of all of the different elements that we're dealing with, that's not a question for me. That's a question for an astronomer, okay, or a physicist, because what they're talking about is how we are creating larger and larger atoms. Remember the periodic table? We've got all those elements that just have parentheses around their atomic masses. Okay, why? That was physicists taking atoms and smashing them against each other, hoping that they would fuse and create a new element. And so they were able to do it. Neat. And I could be, the fusion and fission I always get backwards. So that's kind of a nod in that direction. Kind of make sense? So we're manipulating our understanding of isotopes. How does that apply? This isn't looking at our average masses, though. This is really just looking at how we would calculate. Are we good with that? Yeah, cool. Let's delete it all. Go back to this. This next question says isotope, but that's really just atomic notation, so we're going to scroll past that. Question 18 is really just a rehash of what we just walked through. Interestingly, question 18 gives us that same notation that we saw just 2 questions ago. Okay, and is now asking about the number of neutrons. To answer that question we just addressed, what did we need to be able to know? We needed to know what this notation meant, right? What does this question try to help you with? With what that notation means. Because if you can get this figured out, you could then apply that logic back to this question. You mean you have varying tiers of questions where the questions potentially help each other? Yeah, neat. Okay, which one showed up first? Yeah, the more complicated one. Okay, was that intentional? No, no, it was not. Okay, I build the test, build all the questions together that I want, and then I randomize the crap out of it. Which means which question should you answer first? Okay, easiest is kind of a cop-out. Do a better answer than the easiest. Okay, is the easiest for you the same as the easiest for him? No, so what do you need to do? You need to find the easiest questions. How are you going to find the easiest questions? Read the flippin' test. Okay? You don't need to be super careful on it, but start scanning through it, get an idea of what's going on within the test. Okay? Guess where the most errors happen. There's two really common places where the most errors students will make. The beginning and the end. Okay, what happens in the beginning? Everybody is so panicked and freaked out that you're going to start miswriting all sorts of stuff. And then at the end of the test, you get the exact same issue. You're so panicked and freaked out at the end of the test that you're missing stuff, okay, that you should normally get. My recommendation is those first 5 minutes, you let everybody else panic and you just sit there and read the test. Reading is not a panic thing. Reading is a calming thing. Okay? My strategy once I failed OChem and then came back and went to tests is I would read the entire test first with no pencil in hand. Okay, if I felt really time crunched, what I would double back and do, or not double back, is I would have the pencil and I would star things that I knew I had answers to. Okay, read the whole test through, now go through and pick the questions that I've starred, okay, and now just start willy-nilly going as best I can. Okay, that strategy will help to compartmentalize and make you feel a little bit better early on during the test. It also makes you feel horrible at the end of the test because what you will have found is that the end of the test will have been spent doing all of your time on the questions that you suck at. Okay, which means you'll leave the test only thinking about the things you sucked at. That's kind of painful. Right? But it usually results in a higher score because you tend to neglect or forget all the things that you did a really good job at. Yes, it is on paper. Okay, so the exam will be Wednesday here. We just come in. Once it's time, I'll pass out the test, tell you all to read the instructions. If you haven't read the instructions yet, it's probably a good idea. You do have a practice exam. Okay, scan, read, get settled, and then just take the test. Okay, so question 19. Indium has two common isotopes, indium-113 and 115. Use the periodic table. Which isotope is more abundant? So don't use the periodic table yet. Let's just think through this. If I got two isotopes, 113 and 115, if they were equally abundant, what would my periodic table tell me? It'd be 114. It's dead in the middle between those two values. If the 113 was more abundant, what would my periodic table tell me? The number should be closer to 113. Does that make sense? So what you're trying to do is leverage what you understand about the average process and manipulate that to be able to reason your way through an answer choice. Make sense? So when we go to the periodic table, what does it actually say? Indium, it is 114.82. Which one's more abundant? Indium 115, much closer to the actual value on the periodic table. Does that make sense? Does that work for your isotopes now? Okay. Hey.
Actually, sorry, one more question.
That's okay. I'm gonna set that down though.
Kind of going back to the last one you did with isotopes, is it not maybe better as like kind of a, like to be honest, I did that one on my paper homework and I got it wrong because I thought the answer was phosphorus because the number of neutrons exceeded the number of protons, which to me told me that it wasn't.
So the amount of neutrons to protons as a ratio, generally speaking, is 1 to 1. Okay. And what that does is it falls. I closed the Wikipedia thing. No, I didn't. Falls in what's known as a belt of stability. Come on, jerk. Just do what I ask. I thought I saw it here. Maybe I didn't. Damn it. There it is. So I know this looks crazy, but what we're seeing at the bottom here is your number of protons versus your number of neutrons. And so generally speaking, what we notice is that black thing right through the middle, all those kind of black staircase stuff, is what's known as the belt of stability. Those are isotopes that are stable. They don't explode. Explode is a bit of an exaggeration, but close enough. Okay? The more you veer off of that line, the more explosive it becomes. Okay? But it could still exist. So I could be at a system where I have more neutrons than protons, and it could be way off. Okay? But would I be able to put 16 protons into the same space with 0 neutrons? Okay? So in that scenario, it's coming down to which one's the better of those answers. But generally speaking, it's a 1 to 1 ratio. If you wanted to do nuclear chemistry, you could go study that, and you'd spend most of your time in that top part. If you look here, this is what's known as, actually, I think it might even be this one, an island of stability. That's what they call it, because there's empty space in between. So those elements start to exist. It's kind of neat. Other questions? Okay. Which then brings up the next question. Do you have questions from the practice exam that you would like me to look at? I've been given very general guidelines that I will try to manipulate if you don't tell me to target. Okay. So while you're finding it, I'm going to throw some shade. This document, okay, it was a shared document that you could use to prepare and study for the practice exam. You could put all of your answers into it and you would get feedback into it. I freaked the hell out Friday night because I hadn't opened it yet. Okay, I spent all day Saturday dealing with family is not the appropriate way to say that, but with my family. Okay, got up at 5:30 in the morning Sunday to get into this document so I could provide feedback, and then I scrolled through it and I saw absolutely nothing. Okay, which means potentially a couple things to me. One, you all are rock stars and this is all easy for you and it's not going to be a problem, in which case we should see a sky high average on this. Okay? When we don't see a sky high average on this exam, what do you think my response is going to be? Okay? Why aren't you using the tools that you've been given? Okay? Did you find it yet? You're busy being lectured at. Yeah.
So I did all this on paper.
Uh-huh.
Paper homework.
Yep.
Supposed to also be editing the digital copy too.
So which is a fine follow-up on that. So you can do it for the paper homework. You remember, you're not going to get feedback on the paper homework.
Okay.
All I'm going to do is scan through and yep, that looks like you're showing work. You've explained what's going on. I'm fine with it. Okay. If you want feedback, you can request it specifically. That's now going to be very individual. Even in that very individual scenario, I'm going to say, can you put it in the document so that you can share with other people? Okay. So that everybody can benefit from that work. Okay. You can still say no. That's fine. Okay. But the whole point here is that y'all can work together to make it through the class successfully. or potentially y'all just flounder. Okay?
I want to make sure I understand a quantized system. It was question 25 said which of the following is an example of a quantized system: rainbows, ramps, atomic line spectrum, all the above, none of the above.
Mm-hmm.
And my understanding is like quantized system is when it's not like smooth, it's like jumps. And so I'm still trying to understand also. So I picked atomic line spectrum, and I'm not exactly sure what if that's if the atomic line spectrum is like the lines of light coming, or if it's the energy spheres from electrons.
Both.
Okay.
Okay. So the question for the sake of the recording, because I don't think it's going, is dealing with what is quantized. Okay. And our explanation of jumps makes perfect sense. Okay. The other one that I would use is stairs. Okay. Because stairs provide those places. Okay. I can't take a half step on a stair. If I elevate to that half range, all I do is fall down to the whatever step is underneath me. Okay. So that's a quantized system. A ramp, on the other hand, so we got stairs. Okay. A ramp, on the other hand, I can exist at any one of those spots, right? I can be at any one of those heights. The stairs, I can only be at those distinct, okay, or quantized stages. Kind of, sort of. So when we're talking about that quantized systems, ramps and staircases were used as the examples, physical, real-world examples that we could go through and see. Okay. There's still physical real world examples, but less visible would be rainbows. When we look at a rainbow, okay, what are we seeing? Okay, it's white light passing through and spreading into all the light that makes it up, right? And we look at all the light that makes it up, what we see is the entire spectrum. We see all of the energy levels within the visible range. Okay, that's a rainbow. All of those energy levels is now my ramp. Okay, what happens when we move to the atomic line spectrum? Okay, well, the atomic line spectrum is coming into existence because we have energy shells, and I'm going to draw it a little bit better. First, we'll call that second, third, fourth. So there's my first, second, third, fourth energy levels. And we talk about what's happening with our atomic line spectrum is that our electrons would sit at the lowest energy. Let's just pick hydrogen and say it's at the lowest energy, it's level 1. Okay? And then I pump 20,000 volts of electricity into it. So we give it a crap ton of energy. That energy causes the electron to jump. Okay? So my electron, instead of being at the bottom, will now be at the top of this. Okay? Usually we show electrons with a little point on the head. Okay? That electron now has the ability to relax back down. So it's a higher energy state. Okay? And what it can do is it can fall down. It can go from the fourth energy to the third energy. It could go from the fourth energy to the second energy. It can go from the fourth energy to the first energy. Okay? And if you're like, how can you do that? You've a kid, right? You don't just go down one stair at a time, you go 2 stairs. And you're like, well, can I make it 3 stairs? That's exactly what's happening here. It's a larger energy drop as you make that jump. Okay? That larger energy drop is going to correspond to part of the electromagnetic spectrum. Okay? At this stage, let's just say, for giggles, that this is all visible. You should now be able to tell me which of these is more red and which of these is more violet. How would you do that? What can you tell me about red and violet with regards to energy? Cool referencing frequencies. I asked about energy, and so much so I know nothing about the frequency, so I can't even say if you're right or wrong on that. Sorry. Red is low energy, violet is high energy. You're responsible for knowing which one's high and low energy. So if we're looking at this, which jump is going to be the largest energy?
4 to 1.
4 to 1. If that's going to be the largest energy, I don't have a purple color. This would be my purple jump because that's the biggest jump. Which one is going to be the most red?
2 to 1.
Is it still showing up there? Wow, what did it do? How strange. Oh, came back. Which one's the most red? I heard a 2 to 1. 2 to 1's a little weird because I don't have 2 to 1 shown here. 4 to 3 is going to be the smallest energy jump. That one's going to be the most red. Kind of, sort of? Okay. When we're talking about that electron jumping, it only has those three options. It can go 4 to 3, 4 to 2, and 4 to 1. So what does that mean I'm going to see? Well, our eye is going to pick up all of those simultaneously, because when we excited this, we're not exciting a single atom, we're exciting billions upon billions of atoms, okay, in this system. So our eye isn't going to be able to discern, it's just going to see the blend of all of those colors. But what we can do is put a diffractor up. Did you guys do the diffraction lab yet, or is that today?
I think it's today.
Okay. You can use that diffraction grating, and what you can do is split those out. And what you'll see is it's not going to be a continuous spectrum. What you'll see is lines. What are those lines going to correspond to? The exact energy of each of those jumps. Okay. So the atomic line spectrum are a natural fallout of having distinct energy levels or having a quantized energy system for your electrons. If your electrons could exist anywhere, when they moved from that high energy state to the low energy state, you'd have an infinite amount of possibilities, and that infinite amount of possibilities would result in a continuous spectrum of light. So actually seeing these lines is legit evidence that we have electronic energy states. That's actually kind of cool, I think. Does that help answer your question?
Yeah, totally.
Okay. Go for it.
This is relating to your part of the lab that we're about to do most of us today.
Half of you.
Photons, and we're moving from like the fourth to the first level. You don't emit 3 photons of light or anything, it's just 1. If I was to put 10 and jumping down from 4 to 1, that would be 10 photons still, right?
Yeah, so each of those arrows that we've shown here is emitting a single photon of light. And that photon is part of your electromagnetic spectrum. It's our packet of energy, if you will. So if we're going to go up to that fourth, to go from 4 to 3, that's 1 photon. To go from 4 to 1, that's 1 photon. It just has a higher energy associated with it. But if I excite 10 of these electrons up, I'm going to expect 10 photons when they all relax back down. Kind of, sort of? Does that help?
I got that one wrong.
Okay. Okay, not yet. Different question. 4 to 3, 3 to 2, 2 to 1. Which jump is bigger? 2 to 1. Why? Because Mike, you drew it that way. Okay, and drew it that way because as we go up in energy, those energy levels progressively get closer and closer and closer to each other. So that 2 to 1 jump is the largest energy. Okay, even though you're dropping only one level, the energy difference between those levels is not consistent. Okay. What is the specific energy? Don't worry about that. Just realize that they're different. Okay, and larger or smaller. Okay. Then you said 24. Ooh, cool. I can scroll. Yeah. Okay. So what was the question? Sorry.
I'm
Just
still having trouble like predicting formulas for it, and I mean the active homework I kind of understood that one. I was able to think through it, but this one it was confusing me.
okay. So make sure there's no typos. I don't see any typos, so I think we're okay there. So what this question is asking us about is our chemical properties. Okay, chemical properties may be kind of a challenging concept at this point, except you do have the context for this. Chemical properties are based on electrons, where your electrons are located. Right? Well, do we have a tool that tells us where our electrons are located? That's the periodic table. Periodic table gives you exact context of where the electrons are located. So if did the light just turn off? Okay. If I look at elements on the periodic table, I can tie something about how they're going to react because they're going to react to balance out their electrons, okay, accordingly. Balance their electrons out to what? 8, because of Lewis structure, octets. So this question technically comes about before you deal with Lewis structure, but Lewis structure helps to kind of provide the impotence and the evidence behind this. So let's go through and take a look at carbon and nitrogen right next to each other. Would I expect them to react the same? No. Why not? They have a different number of electrons. How about nitrogen versus phosphorus? Do they have a different number of electrons? Okay. Yes, they do. So when we said that statement that carbon versus nitrogen react differently because they have different electrons, and we now go to nitrogen versus phosphorus, and they have different electrons, how should they react? They should also react differently if that's our analysis. So we have to be really refined within our analysis. So when we're talking about carbon versus nitrogen being different in electrons, what are you very specifically referring to? Their outermost electrons. And you could get away with full outermost electrons. That's actually going to be fine in this. But officially, because we've done Lewis, you should be thinking valence electrons. And we look at carbon. Carbon has how many valence electrons? 4. And we would know that because okay, the numbers at the top of the column. That's perfectly acceptable. Or you could do electron configurations. When we look at nitrogen, nitrogen has how many valence electrons? 5. We look at oxygen, how many valence electrons? 6. Okay, so what we're trying to do is leverage the information we know we have. Within this question, I know carbon, nitrogen, and oxygen. And I know on the periodic table, they're all right next to each other. And then it's asking me about silane. You're not responsible for knowing how to get to silane, which is why we have a generic formula there. We're now asking, how does silicon going to respond to hydrogen? Okay. Well, go to the periodic table. Where's silicon? It's under carbon. So if carbon responded to hydrogen by reacting with 4 hydrogens, what do you think silicon's going to do? Also 4 hydrogens. Why? They have the same valence electrons on the outside. That's what helps to explain a lot of that bonding pattern. This is why Lewis structure and valence electrons become so important, is that we can see these relationships. Okay? We didn't have to see these relationships through an electronic understanding. Our periodic tables were organized according to groups because they observed that when we looked at silicon with hydrogen, it responded the same as carbon with hydrogen. So they started grouping elements based off of their chemistries. What they didn't understand is that they were being grouped not necessarily because of their chemistries, but because of their electrons. Okay? So the electrons became the underlying meaning behind it, and the actual bonding patterns were the end result. Does that help? Okay. When in doubt, if you're looking at this and go, I have no idea how to answer it, realize you have a periodic table. Pull the periodic table out and look for patterns. You're given carbon, nitrogen, and oxygen. You're then told silicon. What does silicon most relate to of carbon, nitrogen, and oxygen? Carbon. It's under carbon, which means, if I gotta guess, let's guess with the one that looks the most like it. Make sense? So in that case, we should be SiH4. column? Yes. Yeah, so we're looking at the periodic table. Alkali metals, alkaline earth, then you get the 10 elements down below as our transition metals. And then you get, I don't know, still don't know, pnictogens, chalcogens, halogens, and noble gases. Pnictogens and chalcogens you don't need to know, but you should know halogens and you should know noble gases, and then our alkali and our alkaline earth. Okay, how do you differentiate alkali versus alkaline earth? True. How many of you want to figure out the number of valence electrons to determine a name? Okay, how else could you figure it out? I think it's dumb. I learned it probably only like 5-6 years ago.
You said alkali is one word, so it's the first one.
Alkali is one word, it's the first column. Alkaline earth is 2 words, that's the second column. I haven't gotten them confused since then. Other questions? So what is electron affinity? What does it sound like? So electron, we're talking about an electron, and then affinity would be, yeah. So we're talking about electrons or electron attraction, if you will. So if I'm going to quantify this, what I'm talking about is the energy released when I take an electron from the vacuum, so free-flowing electron, and I put it into an atom. Okay. What is the ability for the atom to grab that electron and own it? Okay. And that's necessarily going to be a drop in energy, because if the electron's high energy on its own, when it goes into the atom, it's going into an orbital, which by definition is lower in energy. Okay. So there's that loss in energy as it does that. Okay, that could be an emission. Okay, so that's what we're quantifying here when we talk about electron affinity. Okay, so if I'm talking about electron affinity, and I'm an atom, and I grab an electron, what charge? -1. That's it. What if it was ionization energy? That one comes a little bit harder. Ionization energy is the energy necessary to eject an electron from an atom to the vacuum. Okay, so what happened to the atom? It lost an electron, so it is therefore positive. Ionization energy. I'll write that. Maybe not. There it is. I think I spelled it wrong. No? Crap, I don't know. As long, yeah, close enough. Let's just go with close enough. Other questions? Yes.
On 37, I looked up, so my thought was because carbon's a non-metal and copper is a metal, that the bond would be ionic. But when I looked it up, it said it's not.
So, when we're talking about bonds, we've got ionic and we've got covalent right now. That's all you've got as definitions. Okay, when you expand out your rules on what ionic and covalent actually are, those definitions get a little bit nuanced. Ultimately, what you're responsible for are the rules of thumb. What are the rules of thumb? How do you differentiate ionic from covalent? Ionic is a metal and a nonmetal, period. Is copper? Yeah. Is copper a metal? Is carbon, I can't believe I forgot already. No, so that's a metal and a nonmetal, which means that's ionic. Okay? When you start splitting hairs and looking at where those definitions are ultimately coming from, it's about the difference in electronegativity between the elements. That's when things start getting really weird and bizarre. Okay? To that really weird and bizarre system, to be able to do that, what would you need to know? The electronegativities. Tell me the electronegativity for any element you want. Anyone. You don't know any of them? Then don't use that as a rule set. Next question. Sure, why not? Let's do that one. This kind of question gets a little bit out there because you've got to do a couple different things. To be able to decide how many non-bonding electron pairs there are, you have to be able to draw the structure. But to draw the structure, you also need to be able to calculate valence electrons, okay, among other things. So go ahead and take a swing at this one. If you've got questions, raise your hand, and I will come talk to you. I see you. Give me a sec. Fair question. So there's a typo here. It says water, and then it shows pH 3. Okay, pH 3 is what you should be using. It should say phosphine instead of water. Mm-hmm.
It says how many non-binding electron pairs are in the phosphate? So how many non-binding pairs? Like so one over this,
Yes.
two, or just one?
One. That's actually one of the reasons why I picked it. The language can get really confusing.
So you just want to know how many pairs.
Mhm.
So one. So would this be the right way to draw it?
Yeah.
Okay, so then just one.
Mm-hmm. If you got the non-bonding pairs, you got two more questions. What's the electron geometry and what's the molecular geometry or shape? Where do you get your 5 from? Valence electrons for what? Okay. So plus 1, why 1?
Because for hydrogen,
Okay.
one,
How many hydrogens are there?
3.
So should that be 5 plus 1 or 5 plus 3?
I don't even multiply it by 3.
That's what I was going to ask next. Why are you multiplying it by 3?
Because a way I was taught, because I took chemistry last in a different semester online, and that's how I was taught to do it for that time. Was that wrong?
No, it's pretty horrendously wrong, unfortunately.
Okay.
So what is the
I mean, I
point of
could
this
be
3?
remembering it
It's
wrong.
okay.
That could not
It's
be the
okay.
way they taught me.
What is the point of that 3? What does it mean when you're multiplying by 3?
Multiply it by how many?
Multiply what by how many?
This number right here.
That's the 3. What are you
Yeah.
multiplying?
By 6. By how many valence electrons?
Does this 3 say that there's 3 phosphorus?
No.
What is it saying?
It's saying there's 3 hydrogen.
Yep.
So it would just be as an 8.
Yep. Which is going to drastically change the output.
Yeah.
It's okay.
Okay.
Mhm. Next thing to think about, it says pairs. Okay, we will walk through this one all the way from the beginning. So if we're looking at pH3, okay, the phosphorus brings in 5 valence electrons, which we pick off from the periodic table because it's in that 5th column. Hydrogen has how many valence electrons? 1, but I know there's 3 of them. So I can multiply by 3. This gets me a total of 8 electrons. Okay. There are a variety of ways that you can potentially write this information. You'll note that as I go through and do it, I put P and then 5, H and then 1 times 3. Why? Couldn't I have just written 5 plus 1 times 3? Okay. This has a lot to do with where that information is coming from so that you can track your work. 5 plus 1 times 3 is fine, okay? But the problem with that notation is you could very easily start to do this, okay? And not intentionally. So what we're trying to really do is drill into what that formula means and break it down into each of those smallest bits and provide that kind of stacked information all the way through. Okay, it is very easy to fall into other traps and things like that. The whole point of how I'm trying to teach you to do Lewis structure is to cause you to almost formulaically build this out so that your understanding can kind of follow suit. Okay, if we're going to go with 8 electrons, we got to pick a center atom. Hydrogen can't bridge, so it's got to be phosphorus. I'll scatter the hydrogens around the outside, and only because I didn't see very many people go this direction, we'll go that way. Okay, I want to place them around the faces of a square around that phosphorus. That square can be explicit or implicit. It's entirely up to you. That's your personal preference. Okay, I now want to place electrons. Where do I place the electrons? On the hydrogen. I'm going to say no. On the phosphorus. And now I'll be extra irritating because I'm going to say no. In between the hydrogen and the phosphorus. No. Okay, and for people freaking out, I'm being very nitpicky about what you're saying. Okay, why? If I switch the compound to water, are you going to tell me you're going to put the electrons between the hydrogen and the phosphorus? No, because there's no phosphorus there, right? So your words hold power, and when you go through and say, I'm going to place them next to phosphorus, you're missing an opportunity to connect the content to where it belongs. The electrons don't go around the phosphorus, they don't go around the hydrogen. They don't even necessarily go into the space between the atoms. Where do the electrons go? To the most electronegative element. So that every time you solve, if that's your word thought, every time you move to a new question, you're not putting it on an atom, you're associating it with the content. It goes to the more electronegative. In this case, phosphorus is more electronegative than our hydrogen, so we can now start placing them. Once we've identified our most electronegative, now we can start saying, do I have a preference where I want to place them around it? Okay, that's where you could start saying, well, I'm going to place them in the space between atoms. That's fine. Pair. I already forgot. Where was phosphorus? Phosphorus was 5. Okay. I will see people doing this. We got 1, 2, 3, 4, 5 electrons around the phosphorus. Please stop. Okay? If you were lucky enough to be present during the tutoring session, I laid into a tutor for trying to teach it this way. Okay? And it's not their fault because lots of chemists teach it this way. It is inherently flawed and effed up. How many electrons do you place? 8, because Lewis structure is about octets. So I want 8 electrons around the phosphorus. I did feel guilty, appropriately. Okay? Now that I've placed those electrons, I can go back to that total where it said 8 electrons. Have I placed all 8? Yeah, it said 8, so I'm done. No, why not? Okay, so I could now convert things into bonds. So anywhere I have a pair of electrons between atoms, I could convert into a line. I would typically like to go through and erase. I didn't provide myself enough space to just drop it in there. So I can turn it into a line, a line, a line. What do those lines represent? Bonds. And what does a bond represent? 2 electrons. For those people that need organic chemistry, that is flipping critical pieces of information that most students come into organic not knowing because they aren't paying attention to these very simple applications of how we put this together. Because they're very easy to just ignore. Please don't. Okay, now what do? I check octets. Does every atom have an octet? Yeah. Okay. I'd look at the hydrogen. Actually, I have a laser pointer. Let's do that. Boom. I look at my hydrogen. It's got a pair of electrons right there. So that's 2 for hydrogen. 2 for hydrogen. 2 for that hydrogen. For the phosphorus, 2, 4, 6, 8. Everything has its octet. I'm now happy with my drawing. I could now navigate potentially to the question. The question says, how many non-bonding electron pairs are in the phosphine molecule? This is very frustrating as a question, and I've tried a variety of different ways to get at this, and I can never figure out if it's a content loss or if it's just an understanding loss. If it says pairs, a pair is 2 electrons, so I have 1 pair. Okay? If I wanted the answer to be 2, what do I change the question to? Just electrons isn't going to quite cut it because I would argue just electrons is going to turn into 8. How many non-bonding electrons? Does that make sense? So read that question really, really carefully. Again, for sure, it's something I've oscillated back and forth on with the language, trying to improve success on it. And I don't know if it's the wording of pairs or if it has to do with a content loss. Okay, so make sure you're reading that carefully. The next part. What is the electron geometry for phosphine? Okay, so if we were just asked right out of the gate, instead of how many non-bonding electron pairs, just draw the electron dot formula for phosphine, what is the electron geometry? What do you have to do? You have to draw it out. Once you got it drawn out, now what do you do? See, if you had the box drawn around it, you could look at each of the faces of the box and say, does it have electrons? Yeah. All 4 faces have electrons, which means the electron geometry is tetrahedral. Okay, how do you know that? Someone sat down and said that shape is tetrahedral. You have to know that. Okay, so that is something that you should just memorize. Okay, what is the molecular geometry? And this one can be asked about shape as well. They can ask about what's the shape of the molecule, and they'll start to drop off terms. So now the shape is very particularly referring to the bonds. The non-bonding pairs of electrons absolutely contribute to the shape because they prevent the bonds from occupying different space. So they still contribute, okay, but they're not going to be part of the name. So in this case, we have 3 bonding regions, 1 non-bonding region. The name of that is trigonal pyramidal. Okay, you could cheat and say you started tetrahedral with our hand. Okay, right? Did I do this? Okay, the wrist being a group. If I get rid of my wrist, pretend, okay, I still have those 3 not planar. Those 3 bonds are still there, creating a pyramidal shape. It's not planar.
So would it not be bent because if it has four electron groups, it has to have two
So to
bonding and not two of each?
so to be bent, there's a couple different categories that you could get through to get into bent. Okay, so you would have to real carefully read that chart to nail that down. Do you think that's something that you're not going to remember very well? That's a question for you to decide. Okay, so if you decide that you're not going to remember your molecular geometry shapes very well, there's two approaches to this. One, when you start the test, brain vomit to get that stuff down on the paper so you don't have to have it memorized and you just reference it later. I would argue that's a pretty nasty table to have to try and memorize and hold in your head for the whole test or try and draw out. So what might be a good way to ensure that you would get that question right? As you continue to go through the test, that memorization process starts to get weaker and weaker and weaker and weaker. What could you do to help ensure that you could get this question right and you've memorized your table? Find the question first. Okay? So you know that needs a table. You know you're going to see something about it. Scan through the test for something that's asking about those shapes. Find that, answer that first. Now you don't have to worry about it. Now that information can seep out of your brain and you don't have to worry about it again. Make sense? A lot of people packed up, which I think means we're there. Close enough. Okay. If you've got more questions, feel free to come up and ask after class. I will still be holding office hours Wednesday, right? And Tuesday for that matter. So if you've got questions, you can come by and ask. Otherwise, we'll see you Wednesday. Good luck. Is that a question?